Rudinsky, and he will tell us about and he will tell us about weak gauge PDEs, whatever it means, but I hope that we'll understand.
Okay,
Значит,
I will try.
Дим, это куда угодно, лишь бы вот можно вот сюда зацепить. Главное, чтобы вот эта пипочка была где-то там в районе. Let's begin.
Okay, can you hear me?
Yes, I check.
Okay. Okay, so first of all, I am thanks to the opportunity to give a talk here. It's my first time, and the talk is based on my joint work with Maxim Grigoriev. He's here too, but online. And I start with the motivation, and I divided my talk on some points, and the point 0 is.
Проблема техническая, но пока, пожалуйста, пишите вот ниже вот этого уровня сейчас, потому что там сверху штука, и она не убирается.
Okay. Okay. So. So motivation, and maybe I reserve this part of the blackboard to some summary result in each point. So let's start with the notion of PDE and how can we thought about PDE? It can be thought as a pair E and C. This is a C, where E is a fiber bundle over X and C is a subbundle of tangent bundle to E, and it's called Cartan distribution. And this space is a base space of independent variables, and it's assumed that that PDE can be embedded as infinitely prolonged equations, infinitely prolonged submanifold into some into infinite jets of some fiber bundle. Like if we have a fiber bundle X, then we can build jets over it and embed somehow E into respective jet bundle. Then the Cartan distribution becomes canonical. That is, we just take Cartan distribution on infinite jets, and since this is tangent to this submanifold, we can restrict it and get the Cartan distribution on it. Okay, I think everybody who is here knows it's better than me. So let us turn to the next sub point of this point. Let us call B. What is a gauge system in this language? Gauge system can be thought as PDE plus some extra data. Namely, let us consider graded fiber bundle over X. In physics, X is a space-time manifold, or it can be thought as space of independent variables, and F is a graded fiber bundle over X. It means that fiber is each fiber carries its own grading. For the sake of simplicity, let us assume that it's Z grading, okay? And of course, we build jets of this fiber bundle. And here we have some, not some, but here we have canonical Cartan distribution. Let us denote it like dA with respect to some coordinate chart on J infinity F. And an extra structure is what is called a homological vector field. It's a vertical vector field S, which is of degree 1. I will denote degree by ghost, with according to physical literature. And S satisfies the following conditions, namely, S is homological, as I said before, and this is a graded commutator, and S is evolutionary vector field. It means that it commutes with total derivative.
S is the field on F.
Yes, it's vertical. Vertical, yes. No, not on F, but on J infinity. Yes, it's defined not on F, but here. It lives here. And I can use this part of the blackboard. Okay, and what are solutions on this language? Solutions are those sections of X to F whose prolongations satisfy the following equation. So S encodes all information about our system. If our system does not have gauge degrees of freedom, it's not gauge system, then S is just a Kashul-Tate differential, and cohomologies of such a differential just functions which lives on stationary surface in this space. So, okay. This data, what is called local BV system, and I will use this part to bring some meta notions for me and place it here. Okay, so first of all, local BV system. Local BV system is the following data. It's graded fiber bundle with jets and two objects, dA and S. And S satisfies zero, S dA equals to 0, and degree S equals to 1. Okay, to encode gauge system, we need two objects like Cartan distribution and S, right, and BRST differential, and we can replace.
No relation with this PDE which we started.
No. Of course, there is, because S, right, encodes equation of motions, right, like PDE surface. If we restrict ourselves to equation of motions, it means in these terms, in this language, it means that S can be decomposed as delta plus gamma. This guy respects for gauge part of our system. This guy respects for equation of motions. Okay, so if we forget about this part, we know that since S squared equals to 0, right? This guy is called Kashul-Tate differential, and we can reduce our system to cohomology of this differential. Reducing to cohomology of this differential means that cohomology of this differential are just functions on stationary surface of our system. So
may I comment? Maybe it's a bit a confusing point. So there is a definition of solution on the right-hand side of the blackboard, and if you look at it, it means that the prolongation of sigma, if sigma is a solution, belongs to the zero locus of S. So if you take a zero locus of S, this is precisely a graded extension of the underlying PDE. And the body, so if you put all graded variables to 0, the body of the zero locus is precisely the PDE, which is encoded in this data. But in this language, we keep track. It's essentially it's just non-Lagrangian version of Batalin-Vilkovisky formalism. We keep track not only of equations of motion, but also of gauge generators, etc. All these higher structures of gauge algebra. Thank you.
Thank you. So, and we can replace this data, to encode gauge systems, to encode PDEs, we can replace it by some flexible objects, which are called gauge PDEs. They are just such Q bundles. T1x is just a shifted tangent bundle to x. Functions here are isomorphic. The space of functions here is isomorphic to differential forms on x. Yes, and here is some natural homological vector field, which is just a Derem differential, which is understood as a homological vector field here. Okay, so and what is gauge PD? Gauge PD is such an object with Q such that of a degree 1 and which is nilpotent. And Q is I denote the projection by pi, and Q is pi related with differentials here. It means that it is pi projectable to dx on the base. Okay.
Homological field on
dx is homological vector field here. Q is homological vector field on the total space. Yes, and Q is p projectile. It means that it is projected to dx. And I can give an example of such an object. So maybe I want to stress that now instead of two letters which encode our gauge system, we use only Q right here, because Q encodes all the information about our system. Okay. And as an example, let us consider zero curvature equation and Chern-Simons theory. Let us take as E with Q is just
I'm sorry, Dima. I'm right that right now you want to replace one definition to another definition, which is better in some sense.
Yeah, in some sense, this guy is better because it consists of fewer objects than this one, than the left definition, and it's in this sense it's more flexible. It's more flexible because we do not need a DA and S. If we compare this with the definition of PDE, as it was shown that, of course, if we have PDE, we can embed it into one or another jet space, right? This embedding is not unique, right? And in this sense, geometrically, it's not invariant way to think about PDEs. So this object is invoked to fix this, maybe not issues, but
this thing is more invariant.
Yes, more invariant and more flexible in some sense, because there is only one letter to describe a system. Okay, so let us take as an example, let us take the following structure dx, just direct product of G1 Q C E. G is a Lie algebra and G1 is a shifted by one Lie algebra, and QC is a Chevalier-Lemberg of this Lie algebra. Okay, so if we introduce coordinates on E, let us denote it like xa, theta a coordinates on coordinates here, and c alpha coordinates here. Degree of this 1, degree of this 1, degree of this 0. Okay. So then Q has the following form. Q acts on xa like theta a, Q acts on theta a like 0, and Q acts on C alpha like minus 1/2 F alpha beta gamma C beta C gamma. F alpha beta gamma, structure constant of yes, of this Lie algebra, yes. That's how to, this is the way how to compute, I mean, Chevalier-Lindbergh complex, how to compute homology of respective Lie algebra.
Of degree 2.
Yes, this object of degree 2, because Q carries degree 1, C is of degree 1, act by this, we get degree 2. Okay, so this is our Q structure, of course, because of the Jacobi identity, Q squared equals to 0. Yes. And so what, and I didn't say this, but what are solutions in the case of PDEs? Solutions are those sections of T1 x2e which satisfy the following equation, dx. Okay, so here the round differential, here Q field. And let us use this definition of solutions to see what is going on in our example. So let us, in fiber, we have alpha coordinates, right? So let us act by sigma star. Sigma star is a pullback of this section. Okay, so it maps function from this side to this side. And let us act by this pullback on C alpha. So since it carries degree 1, right? So we have only one possibility to make a function of degree 1 on the base. Just multiply some function of x by theta, right? So let us call it like a alpha a of x theta a. And let us combine it like alpha a alpha x theta. It can be thought as differential one form. That's all. And if we apply this equation, right? So what do we get? We get that this a satisfies the following equation: dx a alpha minus 1/2 a alpha equals to 0. Zero curvature equation. That's all. So the elegant way to describe systems, gauge systems, PDEs, and other cases is to encode them to such an object. And but there is a problem, because such objects are, albeit being elegant and flexible in this way, as I told before, they are infinite dimensional, except some several particular cases, like here, because here we see, right, that fiber is finite dimensional, but this is because our system is topological. It's Cherno-Simon's theory, and in the case of topological field series, in the case of finite order PDEs, such objects are finite dimensional, but other cases, this is.
Dima, maybe you should also write down gauge transformations in terms of Q, because otherwise it's.
Okay.
Otherwise, it's not clear why this structure encodes both equations.
Okay.
Differential equations and gauge symmetries.
Or maybe then I delete this part. Okay, we can define gauge transformations are such vector fields of degree -1, let us call it y, such that vertical vector fields of degree -1, such that so we see, right, that this object is of degree 0, right? Because Q carries degree 1, this guy carries degree -1, so this object is of degree 0.
What is delta in this case?
Delta is just transformation. It's formal. Yes, delta is our gauge transformation. If you put this here, you will see that nothing will change. So this is a definition of gauge transformations, and if you apply this definition to this theory, you can get the standard transformations for A.
We forgot about that. That delta.
No. Yes, this is okay. Let me delete this because it's just a decomposition S or intercassultate plus another piece. Okay, I just delete this letter.
Generator of gauge transformation.
Eh? Yes, it is a generator. We can think about it in this way. So if you apply this to this system, I want to write out the resulting gauge transformation for Chern-Simons theory, but you can see that if you apply this definition to the system, you will get the well-known result.
So the commutator is a classical vector field.
Yeah. This is graded commutator of vector fields. That's all. So that's why this system describes gauge system, PDEs, and so on, because we have such guys, these gauge transformations, and these are equation of motions. Okay, but as I said, in general, such objects are.
Who concretely such objects? Who concretely infinite dimension?
Gauge PDEs. If you try, yes, fiber is for infinite dimensional. Fiber. If you try to apply this object, for example, for Yang-Mills theory, which is not topological, you will get, or even for Maxwell, you will get that fiber is infinite dimensional space.
Here, E is a space of fields. Yeah.
Not E. Нет. It's a graded bundle. Space of fields are sections.
No.
Yeah. So okay, so we have some elegant and flexible way to describe gauge theories, PDEs, but there is a problem that in general this object is infinite dimensional. So our main idea is to somehow fix this issue. How to fix this? We can we want to replace this infinite dimensional object by something which is finite dimensional with some relaxation. What does it mean? It means that we replace our gauge PDEs by objects which are finite dimensional, and nilpotency condition of Q field is relaxed in a controllable way. So my talk will be about this replacement. Okay, so let us start from the simplest case, from the maybe some simplest example. Why do we expect that it will work? Let us consider for a moment, for the sake of simplicity, let us consider the case of the category of Q manifolds. Okay, so forget about bundles, forget about Q bundles, graded bundles, and so on. Let us consider category of Q manifolds, and let us relax the condition of Q being homological. It means that Q square is not zero anymore. And let us introduce definition. A triple M Q K, beautiful K, okay, it's like this one, is a weak. Okay, should I recall what is Q manifold or not? Or you know what is Q manifold? Maybe before giving this definition, maybe I need to give.
I don't know who is present at the moment, so it's better to repeat.
Okay. Q manifold is just a graded manifold such endowed with homological vector field. It means that we have a graded manifold M, and Q is a vector field here, such that gradient of Q is 1 and Q square equals to 0. That's all. Graded manifold. Graded means
Z grade.
yes. For now, let us restrict ourselves for the Z gradient. Okay. So Z gradient, space of function is carries Z gradient. Okay. So now we want to relax this condition in some controllable way. So let us introduce definition. A triple MQK is a weak Q manifold. Where M Z graded manifold, Q is a vector field. The space of vector fields I will denote like this, of degree 1. Let me be consistent and denote degree like ghost. 1, and K is a new object here. It's this is an involutive. K is an involutive distribution such that liku K for any V from K and Q squared belongs to K. That's all. Okay, so what is going on here? We
What is LQ?
Lie derivative along Q, just a commutator. Okay, let me replace it like graded in graded sense.
So K is also graded.
Yes, K can be graded.
Also the graded.
Yes. So what is going on here? We just forget about this condition. We relaxed it, but in some controllable way, we introduced this object, which is called involutive distribution. Involutive, of course, is just that two any vectors, a commutator of two any vectors from distribution belongs to the distribution, and we demand that first of all, Q preserve this distribution. It means that commutator for any vector field from this distribution belongs to the distribution again, and that square of Q now not 0, but it belongs to K. Okay. Of course, it can be 0, but 0 belongs to K also. Okay, this is called a weak Q manifold. And why do we need this? We need this, the motivation of this definition is the following proposition that let, without words, just let M UK weak Q manifold. Weak Q manifold. And let A denote a subalgebra of functions on M such that for any f from this subalgebra, and for any vector field from this distribution, vector field annihilate this function. So it's just in some sense a kernel in sense of functions of this distribution, kernel subalgebra in the space of functions. So let us consider all functions which are annihilated by this distribution. Okay, so that's all. Then the following statements are true, that q f equals to 0 for any f from this subalgebra, and q f preserves this subalgebra.
A must not be maximal, just an arbitrary.
Yes, I think yes. I didn't think about this, but I think yes. Maybe you mean by maximal that we have found all generators of such subalgebra. Oh, it should be maximal. Okay, in this sense, it should be maximal. So we have found all the generators of this subalgebra. We generate all algebra. Then okay. So the proof of these statements is trivial enough because this follows from the definition, right? Because square of q belongs to k, so of course it annihilates any functions. And this follows from this fact that since q preserves the distribution and preserve its kernel algebra in this sense. But the consequence of this definition is that if k is a subbundle of Tm, it means that it's regular, has constant rank everywhere, and so on. Then M, we can take a quotient by k as always. Then M is a Q manifold.
Oh, you mean by this quotient somewhat like the space of orbits, yes?
The space of leaves, maybe. Yes, in some sense, maybe you can say like that. But it's simple. This construction is simple enough because how practically we do such quotients. We find subalgebra of functions which is preserved by this distribution, and we can take this subalgebra of functions as algebra of functions on this quotient. That's all. In this sense.
Of course, this holds only locally.
Yes,
Otherwise, we need to assume that it's a vibration.
Yes, at least locally. Of course. Yes, thank you for the correction. Yes, at least locally. I forget about to mention this. So at least locally, MK is a Q manifold, and then it encodes some in our terms, right? Our previous terms, since it's Q manifold, it encodes some gauge system. So this quotient encodes some gauge system. But if from the very beginning M is a finite dimensional space, right? Then the quotient is finite dimensional. That's the main point of this. Okay. So let us turn now to this was just a demonstration of the idea. Now let us turn to the case of category of key bundles but to construct the main object of this talk, let us introduce what is called vertical. We need the following ingredient: vertical jets. I will be brief here, but it's necessary to define it. Let us consider two bundles. And let us consider such restrictions. Let us denote like bx is b p minus 1. Let us fix some x from the base x and consider such restrictions. Of course, no? Okay. Of course, ex is a bundle over bx, right? If we fix x, they are.
ex
Okay.
But bx is restriction of b to x.
to the fiber.
Right.
Yeah, of course. In doing so, we have just a fiber bundle, and we can apply the standard technique to build jet bundle over this fiber bundle, right? But now, since this is a base, okay, roughly speaking, all all equivalence classes will be along direction of this base, okay, like here. So in doing so, we get a standard notion of infinite jet bundle over bx or over ex, and then since x is just a parameter here,
So these are sections which are tangent along the fiber.
along the fiber, yes, exactly. So now we can take a disjoint union pointwise over all axes because it's just a parameter, and by definition, this is called vertical jets over B. And of course, vertical jets is a bundle over E and is a bundle over B. And as always,
Actually, you can have an arbitrary vibration in B and consider
yes.
jets with respect to this vibration. You consider tangency along the
fibers.
along
Yes, yes, exactly. Yes. Okay, since this is just a jet space, we can do the same things like in usual jet bundle. I mean that if we have a section of from B to E, we can build this prolongation like as from B to vertical jets. And with help of this prolongation of section, we can define, I don't know how to say, but I think it's called like total lift of vector field from base to jet space. Namely, if we have a vector field on B, then the vector field it's let us call it tot V vector field on B, then on J infinity V, we have what is called tot V, and it's defined like if we have for any function f on E, we define it like let us call it pullback of this prolonged section on F.
Dima, don't you need it to be vertical on B to prolong? Because it's vertical, these are vertical jets.
You have two operations on jets. You have prolongations and lift from the base space. I don't know how to call this lift, but yes, to prolongations you need that vector field to be a vertical one, and I will say about this. But you can, of course, introduce the operation which is called total vector field. I don't remember the name, sorry, but you can define it like this, in this way, that so they are related by this equation. And namely, if we introduce, for example, coordinates on E, then we have coordinates on J infinity VE, and let us denote coordinate system on E like I don't know, VA coordinates on the base, and some VA coordinates on a fiber. And of course, since everything is a fiber over X, here must be X too. But okay, we forget about this. I mean that if we have a basic vector field on B, which is in coordinates like d over dVA, then we have a lift of this vector field to infinite jets, which is called like dA tot d over dVA. Like in the case of usual jets, here you have d over d along with respect to fibers of B, right, to X, right, exactly. And keeping this in mind, now we can define prolongation of vertical vector fields. To define prolongation of vertical vector fields, let us assume that we have V is already done. So let us denote this vector field as Z. Let Z be a vertical vector field.
But nevertheless, for horizontal lift, you only lift the vertical fields on B. It's just the same like on jets, but everything should be vertical, otherwise you don't have the structure.
You so mean vertical in the sense of B over X?
Of B, yeah.
Yes.
So vertical field on B has a horizontal lift as usual to jets, but only vertical because jets are vertical, and the same with prolongation.
Yes. You mean by vertical vector fields? Yes, because we have two notions of vertical vector fields, because we have vertical vector fields on E, which are vertical in sense that they are along the fibers of E over B.
So, no, but you are talking about vector fields on B. On B, there is only one notion of vertical.
Okay,
because
agree.
B is a bundle.
Agree. Okay, thank you. Agree, yes. Okay, so now if we talk about E over B, so we have vertical vector field on E over B is just a kernel of the projection, right, from E to B, to be precise. And how to prolong this? Prolongation of this is given by new vector field Z bar on vertical jets, which satisfies the following conditions that P infinite V differential of Z bar equals to Z, so it's projectable by, this is a projection from, let me recall. This is a differential of this projection.
Geometrical.
Oh, yes, of course, yes. Sorry. Yes, thank you. And it must be evolutionary. It means that DAV Z equals to 0. Okay, like in the case of standard jet bundle.
So
Z is a vertical vector field on E. With respect to if we have projection E over B, this projection, differential of this projection has a kernel. This kernel is a vertical. This is not. Yeah. Yes, this projection has a kernel. It's this kernel is a space of vertical vector fields. So we can prolong them canonically in this way. They must be projectable. It means that differential acting on this must project this vector field back, and it must commute with the total derivative of this vertical vector field of B over X. Okay, so this is a notion of vertical jet bundle. And now let us fix our B like in our case, in our considerations, in what follows, our B is T1x, is a graded bundle. And doing so, we, and then our E over B is just E over T1x, and then maybe it's useful to write this vertical because it's these are graded jets over graded direction, so the things are different in some sense. Let me maybe introduce a convenient coordinate system on vertical jets of this bundle along fiber of this T1x. And if we have a coordinate system xa, theta a, and psi a here on E, then there is a convenient, a useful coordinate system on vertical jets of E, which looks like xa, theta a, psi bar a 1, psi bar a b, and so on. And these coordinates are related with this one, like if we have vertical projection, then pullback of psi a is just psi bar a plus and so on. Why they're useful? Because in these coordinates, vertical, I mean total lift of d over theta a, right? Because here fibers are thetas. I mean, coordinates in fibers are thetas, right? So the basic vector fields along these fibers is just a d over d theta a. So in these coordinates, why it's useful that lift of this vector field is just a d over d theta. That's it can be checked from these expressions, but that's why they're useful now for our purposes. But of course, the construction is coordinate independent. But for practical purposes, it's convenient to work with these coordinates. And since there is an interesting thing which appears in the case of graded vertical jets, namely that if we have some vertical vector fields, vertical vector field on E, which is not regular, it can be regular on vertical jets. Let me give an example to feel the idea.
Dima, one moment. Let me make a small comment. So this such a coordinates that you wrote are only possible because thetas are anti-commuting. So the fiber of vertical jet bundle is finite dimensional. Yes, and that's why these are just coordinates where Cartan distribution is explicitly integrated. So these are coordinates adapted to Cartan distribution. We can't do the same in usual jets, bosonic, with respect to commuting direction. But because these are anti-commuting, the fiber is finite dimensional, and involutive distribution can be explicitly integrated. So you can find adapted coordinates, and these are precisely these coordinates.
Yes, okay, thank you for the comment, right? Yes, okay. Okay, and the grading nature of these objects leads to interesting features, which we will use later. Let me give an example of such a feature. Let us consider E over T1 R1. Let us take X just be R1. And fiber is given by R12. So in coordinates, it means that if we introduce some local chart here, it's just X, theta, and let it be U, for example. 0, 1, 0. And let us consider the following vector field. V theta d over d u. This vector field is not regular, right? Because if I restrict it to the body of this manifold, it means that theta equals to 0. Then this field becomes 0. So it's not regular in this sense. But if we construct vertical jets of this fiber bundle, then the coordinate system, which is according to this one, is given by X theta u 0 u 1. Here the gradient is -1. Here the gradient is 0, 1, 1. And if you prolong this, this is a vertical vector field. If you prolong this to the case of on vertical jets, then V becomes the following: theta d over d 0 minus d. Now at theta equals to 0, this vector field is not 0 anymore. Because when we prolong such vector fields, we need to commute with total derivative. Total derivative is d over the theta, and it kills this term in theta. So it reduces coefficients in theta. roughly speaking. Okay. So now, but the fun fact that now this vector field is not singular but regular, and this is a feature of this this vertical jets in graded setting. And we will use this later. So, and this example motivates the following definition, that suppose definition that let nu be a vertical distribution on E, and let nu bar its prolongations to vertical jets over E. Then nu is called quasi-regular if nu bar is regular. Okay, are there any questions about this?
So this is definition of quasi-regular.
Yes, of quasi-regular distribution. So, from example, we see, right, that some vertical vector fields, which are singular in this sense, okay, can become regular when we prolong them to vertical jets. So and this gives us many possibilities to introduce some distributions. Okay, so this is I think I finished this part about vertical jets. And now I am ready to formulate the main object which replaces the gauge PDE. Namely, let us call 3 and weak gauge PDEs. Definition. Okay, let us consider such quadruple that ET1X Q K with the following data. Is a graded bundle, Z-graded for our purposes, and Q is a vector field of degree 1, and as in previous case, it's P related to dx. K is vertical, involutive distribution, and K and Q, like in the case of Q manifolds, when we relax the condition of nilpotency of Q, of course, K is preserved by Q. It means that for any vector field from this distribution, Q with V belongs to this distribution. One, and the second one point that Q square belongs to K2. And K is quasi-regular. quasi-regular. So it may be not regular on E, but after its prolongation of vertical jets, it is regular. And this object is called weak gauge PDE. So this 4 objects with this data. This is a weak gauge PDE. So weak gauge PDE is a graded bundle with such a Q and K, such these relations are satisfied. Okay, and now how to define solutions? For example, in this case, solutions are those. Maybe I give it in terms of algebra annihilated by K. So let us again define that A is subalgebral functions of annihilated by K, and then solutions are those sections of E such that for any f from algebra dx f equals to in geometrical terms without any referring to subalgebral functions annihilated by K, we can introduce a vector field along a map. This is called a vector field along sigma, along section. And then we must demand that R sigma belongs to the restriction of our distribution to the section. They are equivalent. They are equivalent. These two definitions are equivalent. Okay. So maybe okay, how much time do I have? I think it's already 1 hour, right? Maybe I...
Up to 9 at least.
Okay, nice. Okay.
You have half an hour for sure.
Nice. Okay, then I can finish my talk. Okay, so once again, summary, right?
How you define a gauge transformation? So you define the solution, and how you define gauge transformation?
Gauge transformations are those vector fields. The formula is the same, but here now another condition on gauge generators that they must preserve distribution.
And you claim that the motivation of introducing some stuff is something will be a finite dimensional.
Yes.
Infinite dimensional. Here, the space of some section should be finite dimensional.
A fiber of this guy, we can pick it as finite dimensional space. Now it consists of, in terms of coordinates, here final dimension of coordinates to describe our system, right? And from the very beginning, since this fiber bundle is finite dimensional, its quotient somewhere will be finite dimensional too, like in terms of like in the case of Q manifolds.
This is the part of the data that's finite dimensional for some coin.
No. In the definition, E can be infinite dimensional too, because you can take, for example, you can take gauge PDE too, right? It's infinite dimensional, but you can endow it by such a K, for example. Just equip gauge PDE by a distribution. It becomes weak gauge PDE in terms of this definition. But now the claim is the following: that if we have finite dimensional E, right, and we have this distribution, then in some sense I will state the theorem that we can take a quotient by this distribution somewhere and get finite dimensional object, which describes a gauge system. Okay, so this is a theorem. Is it clear or no? No? Okay. So again, the data of VGH PDE is the following. So we have gradient bundle. It can be finite or infinite dimensional. We don't know. It depends on this, on our choice. Maybe, I don't know. But the main thing is that we equip it with this distribution, right? And with this defining relations. So now we can relax our nilpotency condition in a way that it belongs to some distribution now. But now if E from the very beginning is finite dimensional, we get the finite dimensional object. And I will give you the statement and give you, maybe I formulate the main theorem. And then I give you an example. Okay. Maybe I formulate it here. Let E T1x QK is a weak gauge PDE. And the prolongation let us name it like n bar of k two vertical jets of E is a fibration. Then weak gauge PDE induces a local BV system, at least locally. Local BV system. Local BV system in this sense. That's why I saved this definition to the later. At least locally. At least locally. So what does it mean? It means that if we have weak gauge PDE with such conditions, so somehow it can induce a local BV system in this sense. So we will have this Berster differential, we will have some bundle over X and jets over it and so on. So maybe I give a sketch of proof. But the important thing here is what that if we start with finite dimensional object, we end up with the finite dimensional object. That's the point. That's the key point here. Maybe sketch of proof. Sketch of proof.
Dima, may I comment about this final? I think it's a bit confusing. So of course, BV system, as you defined it, it's something like jet bundle. which is
Yes.
infinite dimensional. But what I suppose that what you mean is that if vertical jets of your E are finite dimensional, then you take, because it's a fibration, you can go to the base, to the space of leaves, and this one is finite dimensional too, and this is F from the definition of local BV system, right?
Yes, yes, exactly.
Initial
Yes.
bundle, but of course you then take jets. That's where the BLST differential lives, and these jets are of course infinite dimensional.
Yes, jets are, yes, okay, yes. I thank you for clarifying me, because I wanted to maybe clarify it on the example, but okay, nice, thank you. Yes. Okay, sketch of proof that if we have a weak gauge PDE, if we take not vertical but full jets of E, then it can be shown that this is a weak gauge PDE too. This is a weak gauge PDE too. With defining relations that not vertical,
Not
all
vertical,
jets.
top
Now,
jets.
yes, we take all jets.
Okay.
So we will have standard Cartan connection here. Let us call it like K with bar, and of course, maybe I write it like in this way. Maybe it's not inaccurate, but forgive me for this. Okay, so if we take K bar is a prolongation.
Is not N bar.
Yeah.
Okay.
K is a prolongation of
Yes, it's clear.
to the full jets, to the full jet bundle. Okay, so but on full jets we have the decomposition that Q of course can be decomposed as D plus S, right? The horizontal part plus vertical part as always, where D is just a maybe horizontal differential understood as a vector field, is homological vector field. Okay, and from this equation, of course, D with D equals to 0, D with S equals to 0 because S is evolutionary. Yes, and from this relation, we see that from this relation, we are left only with S belongs to K. So vertical part of this Q belongs to K bar. The same we can say about this part. From this relation, it follows that LS preserves K because distribution is vertical, of course, and this is untouched. Okay. And what do we have? Maybe I forget to introduce the following object, which we need. Maybe let me do it on this part of the blackboard. Let us introduce the following bundle. We can consider zero section. Let us call it like as zero, but this okay, alpha. Zero section of x to t1x. This is just a zero section. But we know that vertical jets, vertical jet bundle is a bundle over x2, right? And over t1x, and over t1x. So we can consider pullback bundle along this along this zero section. And we will call this by E bar. In coordinates, this just means that if you remember that our coordinates x a, theta a, and phi bar coordinates.
E bar is restriction of vertical jets.
Yes, to the zero section of x. It means in coordinates, this means that this is just an equation theta a equals to 0. That's all. That's all what it means. And okay, so jet bundle over this E bar can be seen as submanifold in this jet bundle, right? Because we again can pull back them by some projections and so on, and we can realize it like submanifold in this space. Is it clear or no? This is, of course, a submanifold here, but its jets of this guy is submanifold here. No, because we have J infinity E, it's a bundle over E, right? So we can consider pullback of this guy by these projections and embed it. Is it clear or no?
Yes, yes.
Yeah. Okay. Nice. So it's submanifold. Jets of this of E bar can be seen as submanifold in this guy, and moreover, you can see by maybe in coordinates it's easily seen that K bar S and so on are tangent to this submanifold, right? Because it's is defined by this equation. These vector fields are vertical, they are along fibers, so they of course act as 0 on this equation, so they can be restricted to J infinity E bar. K S can be restricted to J infinity V, without V, J infinity E bar. Okay, is it clear? No. I think okay, I think it can be clear, because if we have a submanifold and we have vector fields which are tangent to this submanifold, we can restrict this vector field to this submanifold, right? And let us call this restriction like maybe, I don't know, N0 and S prime, right? But since K is irregular, because yes, quasi-regular, so K bar is regular, and its restriction of regular distribution is regular. So this guy is regular too, and S prime, these defining relations can be restricted to this submanifold, right? So we have a manifold with distribution, regular distribution, and with a homological, not homological, but with vector fields whose square lies belongs to this distribution. But since it's regular, we can at least locally take a quotient and get a Q manifold. Okay, and this is precisely our BV system. This is precisely our BV system. So our BV system resulting will be defined as E quotient by, let us take it as at 0 without bar, because, and sum S bar, and jets over it, because S does not exist without jet bundle. It's defined on jets. Okay, so maybe if I give an example.
Dima, but not E over N, E bar.
E bar. Sorry. Thank you. So thank you for the. Of course. E bar.
Because E you can't quotient. That's the
Yeah,
whole
yeah.
point.
It's just a typo. Sorry. Okay, sorry. Not and zero bar is a distribution which is prolonged from E bar to jets of E bar. But if you can take quotient of jets by this distribution, but this is diffeomorphic to jets of quotient by this restricted distribution. Okay.
May I ask you a question? Is it possible that like different weak gauge PDEs produce isomorphic local BV systems in any reasonable way, in any reasonable sense?
Sorry, once again, please.
Is it possible that different weak gauge PDEs produce isomorphic local BV systems? So different gauge weak gauge PDEs produce the same BV.
Good question. To be honest, I don't know. I think I don't know. I just I can't answer this question.
Maybe I could comment if well, it depends on what do we mean the same. If we are talking about BV up to equivalence, because there is a natural equivalence of BV systems, then of course. If you want to get precisely the same BV system, then the answer is also yes, of course, because you can always add some, you can extend your E and extend your K such that the quotient is the same. You can always add a regular piece to your K, which kills what is there. So of course the answer is yes, you can immediately create infinite number of weak PDEs giving exactly the same. But if you, but it gets even worse if you employ equivalence of BV systems, then of course it's a wild beast, something like this. Yeah, that's the whole point. You can add to E extra variables which sit, which are inside K. You do not see them anyway. That's how it works. But maybe a good example which Dima is going to give, I hope, is finite jets.
Okay, but I wanted to give, of course, not finite jet, but Young-Mills, but I think I can do
any example that supports the necessity of these constructions.
Okay. So maybe I start with Young-Mills, or self-dual Young-Mills, I mean.
Где можно еще поворачивать, имейте в виду. Там есть обратная сторона.
Okay. Yes. Okay. Then I dive into an example. Examples. And I start with self-dual Young-Mills, which is non-Lagrangian theory. So its equation of motion can be derived from any Lagrangian. And as let us construct weak gauge PDE for this case. As X, let us take just Euclidean space R4, right? And if you remember what was in point 0 when I discussed Chern-Simon theory, then we, as a fiber, we take shifted degree Lie algebra as always, and define Q as locally, as always, like qxa, q theta a equals to 0, and q on c alpha, or maybe of course I can contract it with generators of Lie algebra, and maybe without indices it looks like in this way. Maybe to to distinguish commutator of vector fields with commutator of Lie algebra, I put here double brackets, if you don't mind. Okay. Let us consider the distribution K, which is generated by the following vector fields. K without any indices, like AB, A, theta A, theta B, plus 1/2 the metric is Euclidean, so I don't mind about the position of my indices. DC alpha, where alpha is index of Lie algebra. So this is a Lie algebra valued vector field in some sense. Okay, so it's okay. So it can be checked that commutator of Q with such K is without it's some structure constant with C, but I just write it like this one. But it's proportional to K again. So of course Q preserves this distribution, right? So compute Q with K gives K again. Okay, let me be precise. Alpha, beta, gamma, C, beta, K, gamma, A, B. Now with equality. Okay. So Q preserves this distribution, right? Because its commutator with K is again K with some coefficients. In this case, Q square equals to 0, of course, but 0 belongs to K, of course. So when we practically, how do? We just prolong this distribution to vertical jets and then restrict it to the case theta equals to 0, so to 0 section. It's practically without any huge calculations. So in this sense, we get the following vector fields. After prolongation, we will get that distribution, which is prolonged to vertical jets and restricted to the surface theta equals to 0 section of x, x to t1x. We will get the following vector fields: C alpha AB plus 1/2 d over d.
And who are these epsilon?
It's just Levi-Civita symbol. Sorry.
Yeah, that's where Hodge star is hidden.
Yeah,
Of course, you can write more invariantly with the Hodge acting on thetas.
But I think it's more useful to write it in terms of coordinates for our purposes, and that's why we use here R4, right? Because in this case, Hodge star squared is 1, right? And then we have eigenvalues plus minus 1 and can decompose form with respect to this eigenvalues of Hodge star. A, B, C, and the last one, D, DC alpha, A, B, C, D. So we see that this is a prolongation of these vector fields to of the full distribution to vertical jets restricted to zero section, to the submanifold C equals to 0. I mean. And now we need to derive, which is to make a quotient, we need to derive what is subalgebral functions which is annihilated by this distribution. And in our case, this is just okay. Maybe it's useful to write coordinates on this space. It's just xa, theta a, c bar, c a, c bar a b, c bar a b c, c bar a b c d, right? And degree of this 1, degree of this 0, degree of this -1, -2, -3, right? Okay, that 1, 0. And to make a quotient, we need to derive what is in the kernel of this distribution, and the kernel is given by, is generated by xa, of course, because they are vertical. And let me check c bar kernel, c bar, and let us call a introduce ca, and the following combination. This combination is annihilated by this vector field and all remaining two. AB, C, AB minus 1/2 epsilon ABCD. Okay, sorry for CD.
So this algebra A is generated
by these
functions.
functions, right? This is a kernel of this distribution. This is a kernel algebra in sense of functions, and it's generated by these functions. So we can take this algebra of functions as these generators as coordinates on our quotient space. That's what it really means. Okay, so other coordinates are killed. I mean, after taking a quotient, we just drop them out, technically. Okay, and after doing all calculations, starting with Q, prolong it, and so on, we can induce BRST differential on this space of on this quotient. And the BRST differential is given by S acting on F star minus AB, and this is just -1 degree, 0 degree, 1, 0. Of course, this is anti-field in this sense, and it reproduces the action of S on this guy, give us equation of motions, dA AB minus dB AA minus I will define this curve D a bit later. It's just okay. Let me do it here. It's just a total derivative plus it's yes connection in this sense. Okay. So it's just action, right? And acting on fields, our dynamical fields are A's. So acting on A, we must get what? We must get gauge transformations for our field A. And it's given by, Okay, so this is a BRST complex for self-dual Young-Mills theory. And we see that the space of initial, our fiber bundle F, is called here, is finite dimensional, right? And we already have a BRST complex over it. It means that we have jets of it with such coordinates, and S is defined on 0 jets in this way, and it can be, of course, prolonged by the formula that S commutes with dA to jets of these variables. So this is an example of how it works, how it really works.
Dima, can I make a small comment?
Okay.
It's good also to understand that without this BRST machinery, so we started with zero curvature equation. So this zero curvature equation, of course, means that system is topological because you mod out flat connections by pure gauge. But then you introduce distribution, and this distribution tells you exactly that your curvature, it relaxes the equation, the zero curvature equation, so it allows the curvature of your connection to sit somewhere in the self-dual part of F. And that's why you get additional, that's why you get degrees of freedom. The system becomes non-topological because this distribution kills you part of your curvature. This becomes even more transparent if you, for instance, consider gravity, where the respective distribution kills you the part of the curvature, like the Cartan curvature, the torsion and trace path, then you get Einstein equations. So it's even without this introducing these BV complexes and all this machinery, it's immediately clear how distribution makes zero curvature equation or generalized zero curvature equation is to not completely zero. It's very much in the spirit of Cartan geometry, where we ask the curvature of the Cartan connection to sit somewhere in a certain space, in a certain subspace of your algebra. But it's not exactly, you can't really phrase it in terms of normal geometry, but because here this graded stuff is essential. Thank you.
Mm-hmm. Yeah, thank you for the nice. Thank you. Okay, I think that's all. Yeah. I am out of time.
Yes.
Yeah.
No, you are out of time, just in time. Well, thank you very much. Questions, remarks?
Yeah, I have a question. So, from what I understand, roughly speaking, in terms of weak gauge PDE, gauge symmetry is encoded by not only by Q, but by Q and K, right?
Yes, right.
How do you define like gauge equivalence of solutions? If I have two different solutions, how do I know that they are equivalent?
Okay, good question. So if in terms of K, right? So we have another structure like K. So we have two types of equivalence. Like I mean some in like sense algebraic or maybe trivial equivalence, which is an effect effect of this of presence of distribution. I mean two solutions which differs by which differ by such a vector field for K, where K belongs to distribution and gradient of K equals to 0, right? Two solutions are equivalent if they differ by such a vector field. Okay, this is one.
What do you mean by differ?
Differ, I mean that when we defined, right? When we defined solutions, we used something like this stuff. Consider vector field along a map dx sigma bar minus sigma bar q, right? And we demand that R sigma belongs to the restriction of the distribution to this section, right? In terms of algebra of functions, it means that this vector fields equals to 0 on algebra of functions, which is annihilated by this k, right? If we add something to this guy, which has this form, nothing will change, because it lies on the we have leaves along distribution, right? So each solution which differs by the vector from distribution is the same, right? Algebraic equivalence, and we have natural essential gauge transformations, which are given like delta sigma bar y q, where q y is the vertical vector field
these transformations are like infinitesimal transformations, right?
Yes. I'm talking in terms of infinitesimal transformations, right? You're right.
But if I have just two different solutions, how to find out that they are equivalent?
Okay. You mean you? Let me clarify your question.
Kostya, hi. You need to integrate, of course, and there's the theorem that Dima explained is the one that on a right space this distribution can be integrated, and in the examples we see that leaves are contractible, so there is no topology getting in. I'm not sure it's really if you really want global geometry, very general, well-defined, everything, it's easy to say in these terms. But once you go to the superjet space, then you can formulate what you want. Because there, the distribution becomes really regular. And moreover, in the examples which we have, it is a fibration, because it's always along the jet direction, this distribution. But just at the very basic level, I think it's difficult to give very precise global definition of equivalence. So of course, you can always say if it is related, two solutions are equivalent if they are related by a flow of gauge transformation with generator sitting in K. That's, you can say, but it's not very useful. You're right, it's a tricky point, but in the examples, which are interesting examples, all this K lives in a contractible. In all these directions are contractible, and topology doesn't play a role, so everything is integrable. Because it kills the jet directions. I'm not sure if it's very helpful, but...
Yeah. Thank you.
More questions? Okay, thanks a lot. It was a very interesting talk. And
Thank you.
More or less clear. Thanks a lot. I hope this is not for the last time.
Yeah. Thank you.
Thank you very much.
Yeah, thank you. Thank you very much.
Thank you for the attention.